In this lesson, we will be learning about proximity sensors by using these two components to build one. On the left is an infrared emitting LED, and on the right is a 38 kHz photodetector. The infrared emitter LED outputs infrared light that cannot be seen by the naked eye, but can be detected by other electronics. We will be using the reflective property of infrared light to build this proximity sensor, and an LED standoff will be used to shield the emitter. The datasheet for the infrared emitter LED shows that it operates at 880 nanometer and its output emission angle is 16 degrees. Other than that, this component operates just like any other LED that we would use, with an anode pin, a cathode pin, and a schematic symbol that looks like this. To receive the infrared light, we will use this 38 kHz photodetector. The photodetector has 3 pins: power, ground, and output. Its peak detection wavelength is 940 nanometer, and it can run off of a power supply between 2.5 and 5.5 volts. The way the photodetector works is best illustrated by this diagram. First, the infrared signal is detected, amplified, filtered at 38 kHz frequency, and then the signal is demodulated back into its digital 0 or 1 output format. Over here, this datasheet also has an example for how to build a proximity sensor using an infrared LED. First, the raw data is mixed with the 38 kHz signal and then output from the infrared LED. Then the photodetector picks up any reflections from a nearby surface and cleans up the signal for processing. This circuit is very similar to what we will be building. One last note on the datasheet of the photodetector. The peak detected wavelength is 940 nanometer. Our infrared LED emits at only 880 nanometer. This means that while our photodetector will still be able to detect our infrared LED, the photodetector will only be 60% as sensitive to it compared to an infrared LED that emits at 940 nanometer. With the introduction finished, let's take a look at an example schematic for how to wire up a proximity sensor that turns a red LED on whenever something within the proximity range is detected. First, we'll be using the Arduino Nano, and we will need to connect its plus 5 volt power and ground to the breadboard's bus lines. Then we'll connect digital pin 2 to the Vout pin of the photodetector. The photodetector also connects to plus 5 volt power and ground as we saw in the datasheet. Digital pin 3 will connect directly to the infrared LED. Feel free to add a current limiting resistor for safety, but be aware that this may decrease the proximity sensor's range. Lastly, we will connect digital pin 4 to a resistor which goes to a red LED and then to ground. This is the complete hardware schematic for our proximity sensor. This time for the Arduino program, we are going to need to download and install an external Arduino library to get new functions. To get the library, we'll go to gadgetory.com, and in the sensor section, there's the photodetector. At the bottom of the photodetector's page, you can download the library in a zip file. And the easiest way to install the Arduino library is to open the Arduino program, go to Sketch, then to Include Library, and then select Add Zip Library. Choose the zip file that we just downloaded to the desktop, and the library will install. Then I'll restart the Arduino program, and you can tell that the library installed correctly because there are some new examples available that use the IR remote library. That brings us to this lesson's program. First, we'll need to include the new library that we're using called irxremote.h. Then we define the photodetector's pin and the red LED status pin. Here we declare an IRSend object from the irxremote library. This object will assume that the infrared diode is connected to digital pin 3. In the setup function, we set the detector's pin as an input and the status pin as an output. The infrared remote library has a large number of functions related to communication with infrared remote controls. But for this experiment, we only need to set up a single 38 kHz output using the enable IR out function, and then send that signal repeatedly using the mark function. With everything set up, the loop function has only one task: to read the photodetector's output pin and see if it detects infrared light at 38 kHz. If it does, turn the LED on, otherwise turn the LED off. It's as simple as that. So compile the program, load it onto your Arduino Nano, and we'll get started with the experiment. To build the circuit, we'll need an Introduction to Sensors Components kit, a jumper wire kit, and a breadboard. The specific parts from the components kits that we will be using are the Arduino Nano, a 5mm red LED, a 470 ohm resistor, the 38 kHz photodetector, and the infrared LED with its standoff shield. To build the circuit, place the Arduino Nano into the breadboard. Next, using two orange wires, connect both bus lines of the breadboard together, then connect the Arduino's plus 5V and ground connections to the breadboard's bus lines. After that, we connect digital pin 4 to a 470 ohm resistor, which connects to an LED that goes to ground. Next, a yellow wire from digital pin 3 connects to the anode of the infrared LED, and the cathode goes to ground. Lastly, the photodetector connects to plus 5V and ground, and its Vout pin goes to digital pin 2 of the Arduino Nano. And this completes the circuit. So now let's power it up with the USB cable and see how it performs. This yardstick in inches will give you an idea for the effective distance for this proximity sensor. As I block the sensor, the red LED turns on because the 38 kHz signal is reflected back to the photodiode. And as you may have noticed, the maximum effective distance of this proximity sensor is around 7 inches. Proximity sensors are literally all over the place. The most common of which is at the entrance of convenience stores, which have doors that open automatically. And proximity sensors can also be found in bathrooms with automatic paper towel dispensers and water faucets. Proximity sensors are also very common in the world of robotics, both professional and hobbyist alike. The ability to detect nearby objects and automatically perform some intelligent action is paramount to creating anything that must navigate or operate in our human-dominated world.
All parts in this online course were provided by the Gadgetory. Visit them at gadgetory.com/PyroEDU.
Next time in Lesson 5, we will see another use for infrared LEDs in the world of sensors by learning about infrared encoders and building one of our own.